Hey, this is Jack, and this is Lab 4 DC and RC circuits. So the key concepts in this lab were loop rule, node rule, resistor capacitor circuits, RC time dependence, Ohm's law, energy and charge conservation, linearization, and batteries, resistors, ammeters, voltmeters, and capacitors. The key formulas were Ohm's law, node rule, loop rule, and the formula for calculating RC. Um, the assumptions that we made in this lab were that resistance of the wires is negligible and the resistance of the meter is negligible. So part A of this experiment, charge and energy conservation in series circuits. The top right image shows the schematic we used, and the bottom right shows the design I had. So the first part was figuring out theoretically how much current we're going through this, and using Ohm's law, we found it to be 0.02 amps. And when actually applying this to the simulation, we got 0.02 amps. When we replaced one of the meters with a voltmeter, we got the readings of 3 volts and 0 amps, and this was because the reading came before the resistor, so the voltage was unchanged, and the current over here is 0 due to the fact that the voltmeter is what has such high resistance that hardly any current is actually getting there. So the next part was actually measuring the voltage around the resistors and battery. We found 3 volts for the battery, minus 0.96 volts for the 47 ohm resistor, and minus 2.04 volts for the 100 ohm resistor. Summing these all up gave us 0 volts, which shows us that it obeys the loop rule. And right here to the left is more of a diagram of it, increasing in voltage and decreasing with the resistors. And to the right is a diagram showing that the current is consistent throughout the entire circuit. So 2 questions for part A are, why doesn't the voltmeter change the ammeter reading? And I said the resistance of the voltmeter is so high that little current goes through it before it, and therefore has a negligible effect on the current on the circuit. And the second question is, what is reading if the ammeter is connected in parallel with the 100 ohm resistor? And so the diagram to the left here, you can actually see when I plug this in parallel, we get 0.06 amps. And so for the resistance around the resistors, wire, and ammeter, for the 47 ohm resistor, using Ohm's law, we got 47 ohms, 100 ohm resistor, 100 ohms, around the wire and ammeter were both 0 ohms, and right here is the diagram that I was using. For part B, we worked out the RC circuit. Right on the bottom right is the diagram of what we made. The questions were, what happens to the bulb when the battery is connected to the series? My answer was it goes bright and then dims. What happens when the bulb is connected to the charge capacitor? So when it discharges, it goes bright and then dim again. And then what happens to the current in questions 1 and 2? And it's that it starts off large while it's either charging the capacitor or discharging the capacitor, and then decreases to 0 as the capacitor reaches full capacity or 0 capacity. So for the time for the capacitor to charge and discharge in this circuit here, I found that to charge it took 8.18 seconds at 10 ohms of resistance, and discharge was 8.54 seconds. And then for 20 ohms, the charge was 15.69 seconds and discharge was 16.22 seconds. So for part C, the time-dependent voltage across a discharging capacitor. On the left right here, we have the data. Left column is time and right column is voltage at 0.5 second intervals. And right here is the model of the actual setup. So the first graph we have is the voltage versus time graph showing exponential decay. And then on the second graph, we have the this function right here actually graphed so that minus 1 over RC is the slope. And then using that, we're able to calculate that the RC value is 7.95. We found that the real RC value is 6. This is because the data is kind of skewed here at the end, and I figured that was actually because the time intervals were so short and the readings weren't so precise for voltage that it started skewing the data at the end and linearizing at these points, which caused our line of best fit to kind of go off course. So for discussion, the first question was, what if you were doing this lab in real life and use an actual ammeter instead of a simulated one? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So I said a real ammeter has some amount of resistance, and therefore it would affect the current of the circuit as a whole. And then the second question is, what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So in the simulation where the wires have zero resistance, the capacitor would actually charge instantaneously, but in real life, the wires have some level of resistance, and therefore it would take some time for the capacitor to actually charge, even though it wouldn't take very long.